Section 5.4 covers the Fundamental Theorem of Calculus. This is one of the keystone chapters or keystone sections of this entire course. Obviously, the word fundamental there is a big flag to say this is an important section. The big idea is that we want to create a function for finding the signed area under a curve. We'll have some sort of signed area from A to X. This X value is going to be a variable up here. And we want to create a function that determines the signed area based on this other function. What the Fundamental Theorem of Calculus says is that if the function that we're taking the definite integral of, if we let that be continuous on the interval from A to B, and we let the function that gives me the signed area be the definite integral of lowercase f of t dt, then f of x is a differentiable function, meaning I can take the derivative on A to B, and the derivative of capital F of x is equal to lowercase f of x. In other words, what this is saying is that if you want to find the signed area can be found using an antiderivative. The way that we are going to apply this is the following. We let lowercase f be a continuous function from on A to B. Again, that's a closed interval from A to B. We let capital F of x be any antiderivative of lowercase f. If that is true, then finding the definite integral from A to B of lowercase f of x with respect to x can be accomplished by just taking the antiderivative, plugging in the b value, and then subtracting, taking the antiderivative and plugging in the a value. Capital F of B minus capital F of A. This is a really big deal. Obviously, the word fundamental is a flag that shows you that this is a really big deal. This is a keystone section of all of calculus, that somehow, some way, the antiderivative is telling us something about the signed area of a function. Just so that we are aware, this works when lowercase f of x is continuous. If lowercase f is not continuous, then we have to do something different. We'd have to break things up into continuous pieces if we can. So as long as we have a continuous function and we can find an antiderivative, then we can find the signed area using the Fundamental Theorem of Calculus. Like I said, this is a huge deal in calculus. The fact that we can find the signed area of continuous functions using antiderivatives, it kind of blows our mind, because remember, these derivatives had something to do with a tangent line. Now we're saying antiderivatives have something to do with the signed area in some way, shape, or form. I'm not going to show a proof of the fundamental theorem of calculus here, but a lot of places do show a proof of why that is. Our book shows a proof of why that is. I'm not going to test on the proof, but you should know what this fundamental theorem of calculus does, because we're going to use it a lot in this section and maybe in the next couple. Let's compute the definite integral using the fundamental theorem of calculus. The integral is of 3x minus x squared with respect to x from 0 to 3. Let's go ahead and do that. I'm going to introduce some new notation as I go through this. Hopefully it won't throw you off too much. The first thing we need to do is find an antiderivative. Now, it can be any antiderivative that we want, but generally speaking, we'll use a specific antiderivative. If I take the antiderivative of 3x, I would get 3 halves x squared. If I take the antiderivative of minus x squared, I get minus 1/3 x to the third. Now you can tack on any constant that you want to have the antiderivative. I'm going to choose a constant of 0 because that's the easiest thing to calculate with. That eliminates my constant term. Most of the time, we're going to choose a constant of 0 when we find the antiderivative. Now, the notation that I use is the following. Once I've found the antiderivative, I put the antiderivative in brackets, and I put a 0 below and a 3 above. That tells me what I'm going to plug in. This is a very common notation, so it should be fairly straightforward. So here is my antiderivative. The fundamental theorem of calculus says plug in the upper bound into the antiderivative. Let's go ahead and do that. 3 halves times 3 squared minus 1/3 times 3 to the third. After you plug in the upper bound, you subtract what you get when you plug in the lower bound. In this case, since my lower bound is 0, I'm plugging in a 0. We're going to compute each one of these brackets. In the first bracket, you just plug this into your calculator. 3 halves times 3 squared minus 1/3 times 3 to the third. I get a 4.5 in that first bracket. In the second bracket, this is really easy to calculate because 0 times anything is 0. So in the second bracket, I get 0. That means the signed area from 0 to 3 of 3x minus x squared with respect to x, signed area is not approximately 4.5, but is exactly equal to 4.5. There is exactly 4.5 square units of signed area in this. If we were to draw a picture, you would see the parabola pointed down from 0 to 3. So the signed area is all going to be positive since it's above the x-axis. But notice these are not straight lines. So if I tried to do this with geometry, I wouldn't get a very accurate picture. If I tried to do this with rectangles, well, it's not going to be perfect, but I could approximate and get pretty close to 4.5 if I wanted to. With the fundamental theorem of calculus, I very quickly see that this signed area is exactly area of 4.5. I would like you to try this problem. Find the definite integral using the fundamental theorem of calculus. The integral is from 1 to 5, and you're integrating x squared plus 2. Push pause on the video, and in the next video, I'll explain how to do this problem.